Hello everyone. Today we're going to look at the measures of the spread of data. So the standard deviation is the most common measure of spread, which is also called measure of variation. It tells us how varied or how spread out our data are. The standard deviation is denoted by S if it's coming from a sample, and the Greek letter sigma if it's coming from the population. Sigma, we saw capital sigma when we were talking about the formula for the mean. It meant the sum. So this is lowercase sigma, still standing for S, the Greek letter equivalent of S, and that is from standard deviation. We compare values to the mean in terms of the standard deviation to determine if things are unusually high or unusually low. So for example, suppose a data set has an average of 10, or a mean of 10, and a standard deviation of 2. So we're using S, so we're assuming this comes from a sample, but for the purposes of this question, it doesn't really matter. Is the value 5 unusually low? Is 13 unusually high? So we consider numbers to be unusual if they're outside of the interval x bar plus or minus 2s. So from x bar minus 2s to x bar plus 2s, that range is considered usual or normal, and anything outside of it, so anything less than x bar minus 2s or anything bigger than x bar plus 2s is considered unusual. So here's an example that we have. Our x bar is in the middle, that's 10, and if I add my sigma, or my standard deviation, if I add 2 to it, I have 12, and if I subtract 2 from it, I have 8. So the interval 8 to 12 is the interval x bar plus or minus s, and then x bar plus or minus 2s would be, in our case, 10 plus or minus 4. So from 6 to 14 is our usual or our normal interval. And then x bar plus or minus 3s goes from 4 to 16. So again, anything in this x bar plus or minus 2s is considered normal or usual. So if I look at the value 5, that would be right here, and it is outside of my interval. So 5 would be considered unusually low. 13, however, is inside of my interval, so 13 is not considered unusually high. So let's find out how to calculate the standard deviation. The formula for standard deviation depends on if you're looking at S or sigma. So I'm going to put them both up here and we'll see what's different about them. So they both start with the square root of a fraction. The numerator of that fraction is the sum of the squares of the differences between the points x and x bar, the mean. And the only difference is what I'm dividing by. So if I'm looking at S and I'm looking at a sample data, I'm dividing by the sample size minus 1. If I'm looking at the entire population, then I'm dividing by the population size, which we use as capital N. So what we're doing is, again, we're taking an average of the squares of the differences between our points and the mean. And then because we squared them, we want to square root them at the end so that we have the same units. If I squared them, so I just had these, the sum of the squares of the differences divided by either n minus 1 or n, then that is called the variance, and it's denoted by s squared or sigma squared. So we have the standard deviation, and then the square of that is called the variance. Again, because the standard deviation has the same units as our data, we tend to use that over the variance, but we might see the variance come up again. So we're going to do one example. Later on, we're going to show you how to do this in Excel so that you're not going to have to do it by hand. So we'll do one where we don't have too many data sets by hand so that we can see what's actually happening. So calculate S, the sample standard deviation of the following data. So we have 3, 2, 4, 3, 5, 6, 5. What I like to do is I make a table. So I have x, the values, which I've listed. I have x minus x bar, and then I have x minus x bar squared. So down here, this 28 is the total. So I've added up all my values. I have 28. and I need that in order to find x bar. So remember, x bar is going to be the sum, which is our 28, divided by how many values we have. So if I count them, 1, 2, 3, 4, 5, 6, 7, I'm going to divide by 7, and we get that x bar is 4. So our next step is to do our second column, x minus x bar. So 3 minus 4 gives me negative 1. 2 minus 4 gives me negative 2. 4 minus 4 is 0. And then I just keep going. 3 minus 4, 5 minus 4, 6 minus 4, and 5 minus 4. If I do this correctly, then every single time, no matter what my data set is, if I add up all these values, I will get 0. So if you are going to do this by hand, this is a good step to make sure I did it correctly. If I add up my x minus x bars, do I get 0? This is actually one of the reasons why we square the values instead of just taking the average of these guys, because every time I would get 0. So by squaring it, I'm doing two things. One, I'm making everything positive. Remember, a negative number squared is still positive. And I'm also exaggerating the larger numbers. So again, I'm making it positive so that I won't get 0 unless my standard deviation will only ever be 0 if all my values are the same. So assuming they're not all the same, I'll never get a 0. I'll also never get a negative, which is helpful. And again, it's also going to exaggerate any large differences. So I'm going to square my middle column. Negative 1 squared is positive 1. Negative 2 squared is 4. 0 squared, 0. And then again, another negative 1 squared. 1 squared, 2 squared, 1 squared. Now I want to add up all these values. Remember, this is going to be the numerator of the square root that we have for s. So if I add all these up, I have 12. So if I plug this into my formula, I have that s is the square root of 12 over 6. So remember, this numerator is n minus 1. So n is 7, so n minus 1 is 6. That simplifies down to the square root of 2. And then, depending on what I'm doing with this, I could leave it as the square root of 2, or I could do it to some decimals. So we're going to use this again in the next example. So we're going to put this to a couple of decimal places. And we get 1.414. Okay, so again, this is how you would do it by hand, but I will talk about how to do it on Excel later so that we don't have to do it by hand. So the next thing we're going to do is we're going to take our S and our mean that we just found, and we're going to calculate how many standard deviations away from the mean each value is. This is called a z-score, and we're going to see it come up again when we talk about normal curves. So the z-score is x minus x bar over s if I'm talking about a sample, or if I'm talking about a population, it's x minus mu over sigma. Either way, it is my value minus the mean divided by the standard deviation. So if I looked at my data set 2, the z-score would be 2 minus 4 over 1.414, which is negative 1.41. So typically we're going to round to 2 decimal places. Again, we'll talk about this more when we talk about the normal curve. So for now, I'm just going to always round my z-scores to 2 decimal places. My data set 3, the z-score will be 3 minus 4 over 1.414, and I get 0.71. My data set 4, which is the mean, will be 0 because 4 is 0 standard deviations away from the mean because 4 is the mean. For 5, I get positive 0.71, and for 6, I get 1.41. So notice that my 5 and my 3 have the same value, just one is negative and one is positive, and that's because they're both the same distance from the mean, but in opposite directions. So if I'm looking at x minus x bar, if my value is bigger than x bar, then my z-score is going to be positive, and if my x value is smaller than the mean, my z-score will be negative. Also notice that 2 is negative 1.41, 6 is positive 1.41. So again, the fact that they're both 1.41 means they're the same distance from the mean, right? If I just looked at the value itself, they're off by 2. And then 2 is 1.41 standard deviations from the mean. And then 2 is negative because it's below the mean. 6 is positive because it's above the mean. So why do we care about these z-scores? So we're going to look at an example. It says wait times in line A are on average 5 minutes with a standard deviation of 1 minute. Wait times in line B are on average 5 minutes with a standard deviation of 3 minutes. Sarah waits for 7 minutes in line A and Bob waits for 10 minutes in line B. Which is more unusual? So in order to compare things from different data sets, in order to find out which one is more unusual, we will look at their z-scores, because what we're doing is we're standardizing them across different data sets. So we're going to take the z-score for each one, and whichever one is bigger in absolute value is more unusual. Remember, the larger the z-score, the further away from the mean the value is in terms of its standard deviation. The further you are from the mean, the more unusual you are. So for Sarah, her z-score will be 7, her x, minus her mean, 5, divided by her standard deviation, 1. And we get a z-score of 2. So that's right on the edge of that usual or unusual barrier. Bob is going to be 10 minus 5 divided by 3, which is 1.67 rounded to 2 decimal places. So since Bob's z-score is smaller, it is closer to its own mean, which in both cases is 5. So it's closer to the mean in terms of how many standard deviations away from it is. Now if we look at just the numbers, obviously 7 is closer to 5 than 10 is, but that's not taking into consideration the standard deviation. So in terms of how many standard deviations away from the mean the values are, Bob is actually closer, which means that Bob is less unusual and therefore Sarah is more unusual. So let's look at another one. For a certain population of men, the mean height is 69 inches with a standard deviation of 2.8 inches. For a certain population of women, the mean height is 64 inches with a standard deviation of 1.4 inches. Which is more unlikely, a man who is 73 inches tall or a woman who is 68 inches tall? So again, if I just look at the heights themselves, then the man is 4 inches taller than the mean, and the woman is also 4 inches taller than the mean. So to figure out which one is more unlikely, I have to look at the standard deviations. So I don't just want, oh, well, it's 4 inches taller than the mean. I want to know how many standard deviations away from the mean it is. So for the man, his z-score will be 73 minus 69, so x minus x bar, divided by s, 2.8. And I get 1.43. For the woman, the z-score is 68 minus 64 over 1.4. And that gives a z-score of 2.86. So that means that the woman is 2.86 standard deviations away from the mean, and the man is only 1.43 standard deviations away from the mean. So the woman is more unlikely than the man to be 4 inches taller than the mean. And also, the 2.86 is telling us that not even in comparison to the man, the woman is just very unlikely because it's more than 2 standard deviations away from the mean. So we talked about that in the beginning. If you're more than 2 standard deviations away, you are considered unlikely. So that is an unusually tall woman is what this is saying. So read through the section, Let me know if you have any questions on the measure of spread. Bye.